Have you ever wanted to take your MiSTer on the go? Well, now you can. This is my DIY MiSTer Handheld. And today, I'm going to show you how to build one of your very own. A few weeks ago, I released an overview video of my open source handheld MiSTer design called the DIY MiSTer Handheld Model 1. Since then, many people have downloaded the 3D models and started purchasing parts to build one. So today, I want to take you through the build process end to end so you can see how I've gone about making one. But before we start, I want to walk you through a few things that you should be aware of. First, this is an advanced project. The Model 1 requires you to carve up a Super Famicom controller PCB and perform some challenging soldering. If you're a soldering novice, this project might not be for you. You'll be better served by getting some practice on a simpler project first, such as the game badge or the open source cartridge reader. Second, this project requires a 3D printer, and ideally one that can do multicolor prints. I personally use a Bamboo Labs P1S with their multicolor AMS system, and I love it, but you don't have to have the same printer. The shell is 236 by 102 millimeters, so you just need a printer with a large enough build volume to handle that size. The last and most important thing is that while this project is functional, it definitely has some limitations. The main ones are in the area of power and heat. Right now, it has a 5000 mAh battery, and that provides around 2.5 hours of battery life, depending on which core you're playing and what the brightness of the screen is set to. Now, originally, I was planning on putting in an 8000 mAh battery, which would have given around 4 hours of playtime. When I went through the final fitting process, however, I couldn't make the larger battery fit without enlarging the case. So I decided to put in the smaller battery and work on fitting a larger one into the Model 2 design. But aside from the battery life, one of the main power-related issues is charging. When you connect or disconnect the power adapter, the handheld will momentarily lose power and reboot. Now, temperature-wise, the Cyclone 5 dev board does get a little warm. After playing for a long period of time, you can feel the heat on your hands through the casing. It hasn't gotten so hot that it's uncomfortable to hold, and I don't think we're getting close enough to the chip's 125-degree thermal ceiling to be concerned. But I do want to try to fit a fan into the next version. Aside from that, there are some minor nuisances such as lack of control over the screen brightness, and the battery indicator isn't very visible. And it would be great if there was an analog stick, some different button layouts, and if the build process didn't require sacrificing a Super Famicom controller. Alright, with that out of the way, let's go over a list of parts that you'll need. I've included a more complete list with some purchase links in the GitHub wiki for this project, so be sure to use that list when ordering the parts. The link to the repo and the wiki is in this video's description below. First up is the Cyclone 5 dev board. I designed the Model 1 around the QMTech board with the built-in SD-RAM. It's important to grab the version with the SD-RAM built in because there's not enough room to attach a standard MiSTer RAM board. Next, you'll need this 5-inch HDMI display, which I picked up from Amazon for $40. This display is great for a project like this because it operates on 5 volts, and it's relatively easy to pull audio off the HDMI signal. For connecting it to the dev board, I'm using these HDMI ribbon cable connectors. You'll need a straight one, as well as an angled connector that's oriented in this direction. And you'll also need a 10 centimeter ribbon cable, which will connect them together. You'll also need an old Super Nintendo or Super Famicom controller that you don't mind hacking up. We're not going to be using the shift registers on the controller, so a broken controller may work. But you do want to make sure the rubber membranes and the button contacts are in good condition. To run the controller, you're also going to need an ATmega Pro micro board. We're going to wire up the button pads to this microcontroller and use a modified version of the Daemon Byte controller code to present it as a USB controller to the MiSTer. And speaking of USB, you'll want to pick up one of these small USB 2.0 hubs, which we'll modify to fit inside the handheld. For audio, you'll want this PAM8403 stereo audio amp breakout board, which includes an integrated dial potentiometer. And we'll wire a couple of these 1-ohm speakers to it for stereo audio. For power, we're using a combination boost and charge controller. This component has a USB-C port for charging and will allow us to use a 3.7 volt LiPo battery that it boosts up to 5 volts. And for that LiPo battery, we have a MakerHawk 5000 mAh single cell battery pack. Now, this next part is optional, but it's something I do highly recommend. If you want to include an integrated NFC reader, then you'll want to pick up one of these PN532 NFC modules. You'll also need a male USB micro B connector and a male USB-C connector. You'll want versions that are attached to a small breakout PCB, which we can solder some wires onto. It's not completely necessary, but I found that this angled USB-C connector helps relieve some of the strain on the NFC reader's USB port, so I'd also recommend one of these. Okay, those are the big items, but alongside of those, you'll also need a variety of miscellaneous parts. A 2x5 female header, a wired female JST XH connector, a wired male JST PH connector, 3 6mm tack switches, a small power switch, a low-profile heatsink, and some M2 and M2.5 screws. Exact sizes and quantities of these screws are in the parts list, so be sure to check there so you know what exactly to purchase. There are also a variety of consumable materials that you'll need as well. Some double-sided tape, VHB tape, Kapton tape, 30-gauge solid core wire, 30-gauge stranded wire, various sizes of heat shrink tubing, some hot glue, some desoldering braid, and of course, plenty of solder. Alright, now that we have all the parts, let's move on to the build. To start, you'll want to download the 3D models and print them on your 3D printer. I've placed the Fusion 360 source files in the GitHub repo, but the printable version is posted as a set of STLs on both Printables and MakerWorld, so feel free to grab them from either of those places. There are 11 pieces that you'll need to print. The two big ones are the front and back shell pieces. I tried a couple of different color combinations, and this cyan on black print was my absolute favorite. So this is the color scheme that I'm going with in this video. If you're including the NFC reader, then you'll also want to print the card slot cover. We also have a few mounting brackets inside the device. This one goes on the left side of the handheld, and it holds the D-pad PCB and the battery. This other bracket goes on the right side, and it holds the buttons, the microcontroller, and the NFC reader. And this big bracket sits in the middle and acts as a mounting bracket for several of the other components. In addition, you'll also need to print out this power switch bracket, this little USB circuit board cover, and 3 of these tiny buttons, which are used for the standard MiSTer control buttons. Alongside all of this, I've also included a cool looking display stand, so you can print out one of these to keep your MiSTer Handheld looking sharp when it's on display. With everything printed, the first thing to do is to prepare the controller. Start off by opening up the Super Famicom controller and removing the board. Be sure to save the rubber pads, all the buttons, and the 2 metal rods that hold the shoulder buttons in place. You'll need all of these for the handheld. Next, we'll need to remove the plastic connector and the shift register from the controller. I found that the easiest way to remove the connector is to place the controller into a vise and grip the connector with some tweezers. Then add some new solder to the connector's pins and heat them up with your soldering iron while pulling the connector with your other hand. After a few seconds, the connector should just slide right out. For the shift register, you can use a similar technique. Add solder to its pins, and then use your iron to heat up both sides. After a few seconds, the solder should stay hot enough for you to just wipe away the chip. Then you can use some desoldering braid to clean up the excess solder and clean off the flux with isopropyl alcohol. The board should now be clean and flat, with the exception of the shoulder button PCBs, which we're going to leave on there. Now we need to carve the board up. To help with this, I created a cutting template that you'll want to print out on a 3D printer. Just place the controller board into the template and carefully use a sharp hobby knife to score the board along the slots. Run the knife along the cut lines a few times to get a nice deep groove. Be sure to do this on both sides of the board. Next, remove the board from the template and use your knife to score the cut mark all the way to the edge of the board. After you've got a nice groove on both sides of the controller PCB, you can just snap it in half along those grooves. You'll only use the left, right, and bottom center pieces, so you can go ahead and toss out that top center piece. We're going to solder some wires directly onto the traces of these PCBs, so you'll need to grab your scratch pen. Starting with the right side PCB, scrape off the solder mask in this spot to expose the traces for the 4 buttons and the shoulder button. When you clean it off with isopropyl alcohol, you should see some shiny copper traces. If not, go back and scrape off some more solder mask. You'll also want to scrape off this larger trace at the bottom left side of the PCB. This connects to the common pin of each button. Next, take out the board that has the start and select buttons. Here you're going to scrape off the corner of the trace below the start button. Then use a small piece of 30 gauge solid core wire to connect that trace to the button pad below it. The easiest way to do this is to first tin both the trace and the pad with some solder, and then melt the wire into it. Now take out the left side PCB, and you'll want to scrape the solder mask off the 6 traces on the right edge. This will expose the pins for the D-pad and the left shoulder button, as well as the common trace. Next, you'll need to program the Pro Micro MCU. This microcontroller runs a modified version of the Demon Byte codebase to make our hacked up Super Famicom controller behave like a low latency USB controller. First, you'll need to download and install the Arduino IDE. Just head over to the Arduino website and grab the latest version. Once it's installed, go ahead and open it up so we can set up the board. When you're in the Arduino IDE, go up to the Tools menu, select Board, and then choose Arduino Leonardo. Once you've done that, plug in your Pro Micro, and then head back to Tools, and then Port, to select the COM port that appears. Next, we'll need the firmware. You'll find it in the DMH01 GitHub repository under the folder called Code. Download that folder, and once you've extracted it, open the .ini file in the Arduino IDE. Once you're ready, hit the Upload button to compile the code and load it onto your Pro Micro. If everything works as it should, you'll see a message at the bottom of the screen that says it's done uploading. Next, grab some double-sided tape and the right side controller bracket. Attach a piece of tape to the back of the PCB that has the start and select buttons. The right controller bracket has 2 holes in it. You'll need to align the smaller hole with the center hole in the PCB, and the larger hole with the hole on the edge. Then do the same with the button PCB, aligning the upper left and lower right hole with the holes in the bracket. Flip the bracket over and insert the Pro Micro into the socket with the USB port facing the shoulder button PCB. It should be a tight fit so it stays in place by itself. But if it's too loose, then you can go ahead and add a piece of double-sided tape to the underside of the microcontroller. Now you're going to attach some wire to the traces on the button PCB. Start by tinning the traces with solder. For the rest of this build, I'm going to recommend that you use the same color wire that I'm using in this video. This will help ensure that you're making the right connections. Cut off about 15 centimeters of the 30 gauge solid core wire. You'll need green, white, red, yellow, and blue. Strip off about 3 to 5 millimeters of insulation and tin those wires with some solder. Then carefully solder those wires to the traces of the PCB in the order that I'm showing here. The green wire connects to the Y button, the yellow wire connects to B, red goes to A, blue to X, and the white wire connects to the shoulder button. Flip the bracket over and carefully bend back all 5 wires. Use a small piece of tape to just hold the wires in place here. You want to try and minimize these wires moving around to prevent them from breaking off at the solder joint. Next, we're going to solder these 5 wires to the Pro Micro. Start by tinning all the through-hole pins on the board. You want to make sure there's a nice little solder bubble on each one. For each of the button wires, we're going to trim down the wire, strip the end, and solder it to the appropriate pin. First, the red wire connects to pin 15. Then solder yellow to pin 14. The blue wire gets soldered to pin 16, the white wire to pin 10, and the green wire gets soldered onto pin 8. Next, we're going to connect the ground trace from the Start and Select PCB to the ground trace on the button PCB. The best place to do this is at the pads where the shift register was removed. In this case, the ground trace connects to the 6th pad from the left, so we'll add some solder to that pad. And then we'll use a piece of solid core wire to connect it to the large ground trace on the button PCB, which we prepared with solder earlier. After that, we'll need to connect another piece of solid core wire to that same ground connection. For this connection, use a piece of black wire that's around 10 centimeters long. We'll also need to connect a couple of 10 centimeter wires to the Start and Select button. You notice that the Start button is broken out on the 5th pad from the left, so we'll tin that pad and use a piece of blue wire there. And the Select button is connected to the pad next to it, so we'll add a piece of green wire there. Next, we'll fold all 3 of these wires over to the other side of the bracket and solder them to the Pro Micro. The black wire connects to the ground pin, the green wire connects to pin number 4, and the blue wire gets soldered to pin 6. Now you can take out the front half of the shell, and we're going to insert the speaker into the right side. You should be able to just press it into place. Then insert the A, B, X, and Y buttons from the controller, as well as the rubber membrane. Also, find your right shoulder button and slide that into place at the top of the shell, followed by the metal pin that holds it in place, and the rubber shoulder membrane. Finally, set the Start and Select button in place. You can now go ahead and drop in the right controller bracket, and make sure that everything falls into place before screwing it down with 3 8mm M2 screws. Once the bracket's secured, press the shoulder button PCB in place, making sure that it's straight and all the way in. Now we'll go over to the left controller and drop in the 3 3D printed system buttons. After those are in, press the 3 tack switches into the socket face down. They're a pretty tight fit, so it might take some finagling to get them into place. Once they're in, press them down as far as they'll go. Then we're going to connect all 3 buttons to a common ground using 2 pieces of short, black, solid core wire as I'm showing here. Then on the innermost button, connect a longer piece of black wire that's around 25 centimeters in length. Next, we'll attach a 25 centimeter colored wire to each of the 3 buttons. The innermost button will get a blue wire, the middle button gets a green wire, and the last button has a yellow wire. To help hold these wires in place, we'll use just a little bit of hot glue. After that, you can press the other speaker into place, and we'll then turn our attention to the D-pad PCB. We're going to solder wires to the D-pad PCB just like we did with the other PCB. So start off by tinning those exposed traces with some solder. We're going to attach some longer pieces of wire to this board because they need to reach across the shell to attach to the Pro Micro. So make each of these wires around 30 centimeters long to give yourself some extra room to work with. Start off by attaching the black wire to the thicker trace closest to the bottom of the PCB. This will connect into our common ground. Then, working from the bottom up, connect a white wire to the right button. The green wire's next, and that connects to the left button. Then a yellow wire connects to the down button. Use a blue wire to connect to the up button. And finally, a red wire for the left shoulder button. We can then go ahead and drop the D-pad from the controller into the shell, followed by the rubber membrane. Next, take the left shoulder button and slide it into place, followed by the shoulder button membrane. Place the D-pad PCB down onto the button assembly, and then cover it with the left controller bracket. After making sure everything's aligned, use 3 8mm M2 screws to tighten down the bracket. Just like on the other side, press the shoulder button PCB into place, and drop the metal pin into the hole to keep it all together. Now you want to take the 6 wires attached to that board and push them into the groove that runs along the top of the shell. This will let you run them across the case without them getting in the way. Once they're in there, cover the groove with a piece of Kapton tape so they don't pop out. We're now going to trim down each of these wires and connect them to the Pro Micro. Start by soldering the blue wire to pin A0. Then solder the yellow wire to A1. The green wire connects to pin A2. White goes to A3. The red wire gets soldered to pin 9. And finally, the black wire connects to the ground pin. Now we're ready to install the screen. The screen will be powered from the 5-volt fan connector on the QM-Tech board, so we'll need to install a JST-XH connector on the screen. Trim this connector down to about 5 centimeters and strip a couple of millimeters off the end. We're going to solder the black wire to this capacitor between these 2 chips on the back side of the screen. So start off by adding some solder to the side of the capacitor that's closest to the edge of the PCB. Then you can go ahead and carefully solder the black wire to it. The red wire will attach to the metal casing on the USB connector, so add some solder to the outside of that connector. Then cut down the red wire, strip it, and solder it to the USB casing. Next, take out your angled HDMI connector and the 10cm ribbon cable. Insert the ribbon cable into the connector and clamp it down. Then bend the cable back behind the connector and use some Kapton tape to hold it into place. Once you've done that, place the HDMI connector into the screen. Now you can go ahead and drop the screen into place. Cover the screen with the screen bracket, making sure to run the wires for the system buttons and the speakers under the bracket. There's some clearance underneath, so the wires shouldn't be pinched. You can then use 4 8mm M2.5 screws to fasten the bracket into place. For audio, we'll use this PAM8403 stereo amplifier module, which has a built-in volume dial. We'll need to first remove this pin header and the speaker connectors so it'll all fit into the case. I found that the easiest way to do this is with a vise like this one. In fact, I'll be using this vise a lot for the rest of this build, so you might want to go ahead and print one out for yourself. There's a link to the 3D object in this video's description. Clamp the board into the vise upside down and add some fresh solder to the solder joints for the pin header. Then use some pliers to gently pull down on the header while heating up the solder joints with your iron. After a few seconds, the pin header should just slide right out. Then rotate the board and do the same procedure with the green screw terminals. Go ahead and set that board aside and get out the USB hub. We'll need to start off by cracking it open, removing it from the case, and putting it in the vise. You'll need to desolder a few of the connectors, starting with the uplink connector. We'll then remove the 2 female USB connectors that are facing out to the side. You can use the same technique as before. Add solder, and then pull the connector away from the board while heating up the solder joints. After cleaning up the board, we'll need to cut away the small portion that I'm showing here. Make sure you leave all 4 USB pins on the board. The portion we're cutting off is just a piece of the ground fill. Because this piece is small, I found that it's best to score it with a hobby knife, and then cut it off on the score line with some snips. We're going to reuse the male USB connector that we removed earlier, so we'll need to remove it from its case as well. Once you do, go ahead and desolder the little wires attached to it. Instead, we're going to solder on some longer wires, so tin those pins and solder on some stranded 30 gauge wire. Again, you should use the same colors I'm using to make it easy to follow along. Next, we'll prepare the power switch. Secure the switch in the vise so it's held steady while you work. We'll need 2 black wires, each around 10 centimeters long, which should give you plenty of slack to work with. First, solder the 2 black wires together at one end. Once they're connected, solder that end to the middle pin of the power switch. Now take another wire and solder it to one of the remaining pins on the switch. You can see that I used a black wire here, but I'd actually recommend using green instead. That way it's easier to tell this wire apart from the other 2. Alright, next we'll install the boost and charge controller. Insert the controller into the bracket by sliding the USB port through the opening in the shell and seating the board into the socket. Once everything's aligned, secure the left side with a 4mm M2 screw. Next, slide the audio amp module into the next slot on the bracket. You want to make sure that the dial pot can move freely and doesn't rub against the opening in the case. The module should fit snugly into place, but if it's a bit loose, go ahead and add some double-sided tape. After that's in place, go ahead and add another 4mm M2 screw into the hole next to it. And the last socket on the bracket gets our USB module. Insert the USB connectors through the openings in the case, and then press the module into the socket. Don't worry if it feels a bit loose, we'll take care of that in just a little bit. Okay, we can now start wiring these modules together. First, we need to tin the battery pads on the charge controller, as well as the 5-volt output pads. Then take 2 pieces of stranded wire and solder them together. You'll want these wires to be around 10 centimeters long. Once you've done that, solder these 2 wires to the positive 5-volt pad. Then tin the VCC pad on the audio amp and trim one of the red wires and solder it to that pad. Next, we're going to install a female JST PH connector for the battery. You'll want this connector to be somewhat short, so cut it down to about 4 centimeters. This connector should come off to the side, so when trimming it down, make the black wire longer than the red. Then solder the red wire to the positive battery pad and the black wire to the negative pad. Then grab your power switch and insert it into the hole to the left of the charge module. The power switch cover sits on top of it and gets secured into place with 2 8mm M2 screws. The power switch should stick out the top and slide freely. Now we're going to take one of the power switch's center wires, trim it down, and solder it to the ground pad on the audio amp. You can see here why I recommended using a different color for the non-center wire. Since all my wires are black, it's difficult to tell if I'm soldering the correct wire here. Then take the non-center wire, which should be the green one if you followed my earlier advice, trim it down, and solder it to the output ground pad on the charge controller module. Next, we're going to tin the right input, ground, and left input pads on the audio amp so we can solder on some stranded wire. Use a white wire for the INR pad, green for the ground pad, and yellow for the INL pad. These wires need to be long enough to reach over to the audio jack on the screen. You'll want to solder these wires to the exposed contacts on top of the jack in the order that I'm showing here. Okay, now we're going to prepare this 2x5 female pin header. This will be used to connect the QMTech FPGA board to our system buttons, as well as power and ground. Start by bending back both rows of pins on this header so they're at a 90-degree angle, sticking straight out from the side. We then need to bend these 2 pins together with some pliers so that they're touching one another, and then we'll connect them with some solder. We only need a few of the pins on this connector, so use some pliers to pull out the pin directly across on the edge, as well as the 3 pins next to the ones we just soldered. Then go ahead and tin the 4 pins on the opposite side of the connector with some solder. Now we're going to place this header into GPIO1 on the QMTech board in this location. There should be 4 sets of unconnected pins to the right of this connector. Set the QMTech board next to the shell, and then solder the remaining black wire from the power switch to the 2 pins that we soldered together on the header. Then, trim and solder the second red wire from the power module to the header pin directly across from the black wire. We'll then go ahead and solder the wires from the tack switches we installed earlier to the next 3 pins. First green, then yellow, and finally blue. And then we'll take the black wire that connects to all 3 of the tact switches and solder that to the other black wire on the header. Remove the header from the QMTech board and bend back the pins so they're sitting flush against the side of the connector housing. You can see here that I just used some pliers to bend them as far as they would go. We'll then put some hot glue on these pins to keep them in place and to prevent the thin wires from breaking at the solder joint. Next, we're going to connect the speakers to the audio amp. Start off by tinning the 4 speaker connection pads on the module. Then grab 2 red wires and 2 black wires about 10 centimeters each and solder those onto the pads in this order. The wires on the speakers aren't long enough to reach across the device, so we'll use these to extend them. Then we'll trim those wires and add in some heat shrink tubing and splice them into the speakers. Now we'll make a short USB uplink cable for the controller. For this, we'll use this micro USB connector that we can solder some wires onto. The connector that I'm using here has 2 pads on the top side and 3 pads on the bottom. Place the connector in your vise with the bottom side facing up and tin the 3 pads with some solder. Then, working from right to left, solder a 20 centimeter red wire on the first pad, a green wire on the second pad, and a black wire on the third pad. Then turn the connector over and solder a blue wire to the pad on the far left side. Next, we'll need to bend the wires at a 90-degree angle like I'm showing here. And to keep it in that position, we'll use some heat shrink tubing on the wires. We'll also use a smaller piece of heat shrink on the connector itself to help secure the wires to the pads. And then a slightly larger piece of heat shrink around the plastic housing just for some additional stability. Now we're going to repeat this procedure, but this time on the USB-C connector. You can see here that the connector I'm using has 2 pads on one side and 5 pads on the other. We'll start off with the side that has 5 pads by tinning the 2 middle pins with some solder. We'll solder a new 20 centimeter piece of blue wire to the middle pad on the right and a green wire to the pad just to the left of it. Then we'll flip the connector over and tin both pads on the other side. We'll then solder a black wire onto the right pad and a red wire onto the left one. And like the other cable, we'll use heat shrink to keep the wires in place. But this time, we're going to keep the connector straight instead of bending it. Okay, now we'll go ahead and insert the micro USB cable into the controller MCU. We're going to solder these wires to the first unpopulated connector on the USB hub board. So we'll start off by trimming them down to the right size. And we'll strip the end off each wire and tin them with some solder, as well as the pads that we'll be attaching them to. Then, starting with the pad closest to the USB connector, we'll solder on the red wire, followed by blue, green, and then black on the end. Next, we'll install the USB uplink cable, so we'll need that USB-A connector we prepared earlier. And you can see here that I'm adding some heat shrink on those wires to keep everything in place. We're going to solder it to the small set of downward-facing pads on the USB hub. You'll recall that these are the pads we removed the connector from initially. We'll first need to tin these pads with some fresh solder. Then, working from right to left, we'll attach the black wire to the pad on the far right. Then the blue wire next, followed by the green wire, and finally the red wire on the end. Now we'll take out the QMTech board and place the copper heat sinks on the FPGA. I've tried a few different heat sinks, and I think these copper ones work out the best. They're low profile, and when you arrange them in a 2x2 grid like I'm doing here, it gives them a little bit more surface area to dissipate heat over. This next part is a little bit tricky because the wires are kept as short as possible. You want to position the QMTech board upside down so that GPIO1 is at the top side of the device. Then take that 2x5 header block and install it on the GPIO1 header in the same position as earlier. Since the board is upside down this time, you want to place it on the 5th pin from the left, as I'm showing here. Then on the side of the board, we'll plug in the JST-XH connector from the screen. And we'll move the HDMI ribbon cable out of the way as we set the board into place. Now we'll attach the other end of the HDMI ribbon cable to a straight HDMI connector, and we'll need to fold the cable and insert the HDMI connector upside down into the HDMI port on the QMTech FPGA board. Then we can go to the other side and plug the USB uplink cable into the USB port. Next, we're going to install the NFC reader, so take out the NFC module and insert the angled USB-C connector. We'll then place the module upside down on the standoffs with the angled connector facing inward. And then we'll screw it into place with 4 6mm M2 screws. We'll then go ahead and plug in our USB-C cable, and then we'll trim the wires and solder them to the other unpopulated USB port. This time, however, the wires need to be soldered in the reverse order, so solder the black wire to the pad that's closest to the USB port, followed by the green wire, the blue wire, and then the red wire on the end. Now we can add the cover plate to the USB hub. Just press it into place and secure it with a single 4mm M2 screw. The last thing we'll need to do inside the shell here is to install the battery. We'll use some double-sided VHB tape to secure it into the bracket and keep it from rattling around. This tape is really good for this type of application, but it's very difficult to work with, so don't expect it to be pretty. We'll then plug the battery into the connector and tuck in the excess wire. Okay, now take out the rear cover plate as well as the NFC slot. The slot will attach to the cover plate using the 4 recessed screw mounts. Positioning them is a little bit tricky, but you'll need to line up the holes and then screw it in place with 4 4mm M2 screws. We can then place the rear cover onto the shell. But notice these post mounts near the edge. These slip over the pins that hold the shoulder buttons in place, so we'll need to make sure that it's lined up correctly. Once the cover's on, use 4 8mm M2.5 screws on the inner 4 screw holes. These screws will not only keep the cover secure, but they also go through the QMTech FPGA board and secure that to the bracket inside. Then we'll need to use 4 10mm M2.5 screws on the outer 4 screw holes around the edge of the shell. And the very last step, of course, is to peel off the protective film from the display. You can then take your MiSTer microSD card, insert it into the slot, and turn it on. Assuming everything works as expected, you should see the MiSTer menu. Now, one thing to keep in mind is that you may need to set up the buttons on your controller before they'll work correctly. To do this, you may need to plug in a USB keyboard and use it to select the menu option called Define Joystick Buttons. Also, if you don't hear any audio, you'll need to make sure the global volume setting in the MiSTer menu is turned all the way up. We're using the dial on top of the handheld to control the volume through the speakers, so there's no need to change the global volume again after setting it initially. Alright, that's it. By carefully following the instructions, and with a bit of patience, and a little luck, you should now have a functioning handheld MiSTer. Thanks for watching. I'll see you next time. But, as always, until then, go make something cool.